Hello everyone, welcome to lecture 35. So in the previous class we were studying a bit about surfaces, surface energies. We came from the fact that liquids have some internal pressure inside them, right. So coming because of the surface energy, and this happens when surface energy surfaces start to equilibrate, right. So we proved that Young-Laplace equation. And then we said solids also have similar sort of internal pressure, but the difference between solid and liquid is solids have anisotropic surfaces, right. So they have different phases have different energies. We have calculated some of these things, right. So gamma 100, gamma 111, gamma 110 of a causal crystal, of an FCC crystal, right. We answered the question why densely packed planes have the least surface energy, because the bonds that are dangling out of that plane are very less in number, so it is easy to cut them, right. And then so then we started looking at what are so different surfaces have different energies. So in general I am answering an anisotropic surface energy problem when I move to solids from liquids. And then we said if there is a small miscut, so if I grow a single crystal, an ingot of single crystal, and cut it off, so it is unlikely that I am just cutting it at exactly 90 degrees. There is bound to be some error within that 90 degrees, right. So I am not cutting it at 001 axis, perpendicular to 001 axis. I will be cutting it at 89.9 degrees to the 001 axis, and that will give me a vicinal surface. That is not going to give me a singular surface, right. And this vicinal surface is made up of several such so it's not going to be a plane that is just at 89.1 degrees. We will see that in today's class. It's going to be a set of various different planes exposing both the 001, you can see here, right. So exposing both the 001 as well as the 100, 100, 001, 100, 001, 100, and so on and so forth, right. So both these are low surface energy planes. So it wants to expose low surface energy planes, it wants to minimize the total surface energy, but overall so I get this angle which is what is known as the Miscut angle, theta. Okay, so theta is called the Miscut angle. Okay, now before going into details about so how surfaces split, etc., I take a cube like this. This is, let's say, a causal crystal. A causal crystal has 001 faces, which are the most least surface energy faces. So for example, this surface has least energy, this surface has least energy, this surface has least energy, and so on. And then I cut this cube along this plane, right, and that is the 111 cut, right. So I take a cube and I slice it along the body diagonal, right. So I do a 111 plane cut, right. So it's okay. So this is the 111 cut. Now when I do a 111 cut, it turns out so this cube gets rearranged into several of these surfaces, right. So it's not exactly atomistically, I don't have a nice 111 plane here, right. Atomistically I seem to have several such 10001 and so it gets cut into several of these cubes, giving me this face, and this face, right. So they are the least surface energy faces. So it gives me this, right. It gives me all these low surface energy planes. Okay. Now we will see that it's not always the low surface energy planes. Sometimes the second higher surface energy planes, sometimes the third higher surface energy planes can also get exposed, right. So we will actually look at a construction called Wolf construction to see what are the various planes that get exposed, so when I cut crystals or when I make crystals, right. But so in general when I cut, it's not always true that in an atomistic fashion, right, I get a nice cut like this. I always get these steps, and these steps we call them as terraces. Okay. So here also you can say that these are nothing but some kind of terraces in 3 dimensions, right. Okay. Now so let's say I have a terrace like this. This is my this is the surface, right, and this is a surface, a vicinal surface. A vicinal surface has a terrace like this, but so I can have a more structure to the terrace. It's not just something like this. Even in this direction I can have a terrace like this, right, and when I combine them both, so I get what is called I get this sort of a shape. You can see it here. Where is the eraser? Okay, eraser, right. So you get this kind of a shape, right. I will use the pen. Yes, so there is a cut here, there is a cut here, right. So both of them combined, so I get several types of terraces. They can combine to give me these kinds of newer shapes. Okay. Now this kind of a shape of a surface defines for me several positions, several atomic positions. And essentially what I am interested in is, so eventually I want, so if I look here, so on a surface like this, I have all these atoms that are coming and falling on my surface. They are going to diffuse around and they are going to find a place to get stuck, right. So this is very important for atomic diffusion on the surfaces, and this atomic diffusion on the surfaces happens during the growth, right. So especially when atoms are coming from gaseous phase or plasma phase, falling onto my substrate, they are getting sprinkled onto the substrate, right, and then they move around, and once they move around, so at high enough temperatures, at reasonably high enough temperatures, then they go to the terraces and they get stuck there. And especially if this terrace has a finer structure, so which position does it get stuck to is what allows us to do some thermodynamic calculations on this. Okay. Now for example here, 5 different positions have been marked, right. So 1, 2, 3, 4 and 5. Okay. Now let us see what is the difference between each of these positions. Okay. So let us say, so I will say refer to the presentation, you remember this, right. So 1, 2, 3, 4, 5. Okay. Refer to the presentation. Okay. Let us talk about site number 5. Okay. Now site number 5 or site number 1. Okay. So for the time being, let us talk about site number 1. Okay. In site number 1, right. So let us say what is, site number 1 has an atom, add atom that has, so has an atom there, right. Now how many dangling bonds does this site number 1 have? Site number 1 only has one dangling bond. This is the one dangling bond that comes outside, right. Oops. When I am talking about surfaces, I really want to talk about dangling bonds. So the number of dangling bonds in site number 1 is 1, and the number of non-dangling bonds, which means the number of bonded bonds are 1, 2, 3, 4 and 5, right. So the other 5 5 is this side, right. So the other 5 sides of the cube, the other 5 faces of the cube are bonded, one face of the cube is unbonded. So I have one dangling bond, right. Which defines the surface energy plus 5 bonded bonds, which does not mean much, but so okay. So this defines the surface energy. Essentially these contribute to lowering of surface energy, this thing contributes to higher surface energy, right, in that local region, right. Now let us say I desorb an atom from site 1. So when I desorb an atom from site 1, which means I am plucking out an atom, right. So the atom goes, this atom, right, so which is colored here is going and then joining the let me put full screen. This atom goes and joins the environment, right. So or so there is a gas phase, this is the solid phase. The solid atom is going to join the atom in the solid phase is going to join the atom in the gas phase. Okay. So at some point I am going to look at gas solid equilibrium, right. So but so initially I am going to say that there is a desorption process, means I am actually detaching this atom and then this atom is going and joining the vapor phase. alright. So, now in the desorption process which happens, right. So, it is not just adsorption, I can also have desorption. So, my growth is atoms are coming, but atoms are also leaving, right. So, my growth has both components to it. Growth has both adsorption and desorption components to it, right. Eventually, I want adsorption to be more than the desorption. So, some atoms are coming, right, some atoms are leaving, right. So, all these processes are happening when the growth process is happening. Okay. So, so at an atomistic level, I am looking at some kind of an atomistic picture here, right. So, in that sense, I am desorbing an atom from site 1. Once I desorb an atom from site 1, you see, so there was an atom here in 3D, right. So, I have desorbed it. I have desorbed it. By desorbing it, I am actually creating 5 dangling bonds. Earlier there was just one dangling bond, now I have desorbed it. So, this is dangling, this is dangling, this is dangling, the other two faces, you know, so that I did, this is dangling and the one on the other side, right. So, that is also dangling. Okay. So, instead of one dangling bond, now I have created for you 5 dangling bonds. Okay. And you know, so desorption, the process of desorption is going to increase the surface energy. Okay. Okay. Now, what about the process of adsorption? Adsorption means I you know, there is this site, the atom comes and gets stuck to that site. Okay. So, the process of adsorption is also going to create for me 1, 2, 3, 4, 5 dangling bonds. So, that is also going to increase the surface energy. Right. So, any sort of addition or subtraction of atoms from this position is going to increase the surface energy for me from the starting, you know. So, surface energy increases either with desorption or adsorption. On site 1. Okay. Now, let us look at site 5. Okay. So, shall we look at site 5? Site 5 is this other extreme, right. So, where if I remove one atom, right. So, initially I have 5 dangling bonds. If I remove one atom, I have 1 dangling bond. So, the surface energy has reduced. Okay. So, let us say to site 5 desorption is going to reduce the number of dangling bonds from 5 to 1. Okay. Whereas, adsorption, now adsorption means where am I adsorbing, right. So, I have so many positions here. So, I can either get adsorbed on the top of this, right, or I can get adsorbed here, right. So, or to this side, whatever, right. So, different adsorption has different number of dangling bonds that it exposes to, but let us say I am adsorbing to the top of it, right. So, one atom is coming and getting adsorbed on the top of it, then I have 1, 2, 3, 4, 5, 6, 7, 8 dangling bonds, but 8 dangling bonds per 2 sides, right. So, essentially you know, I am still changing the surface energy. Okay. So, I am creating now 8 dangling bonds over 2 sides. Okay. So, I think let us just again to be sure count it. Okay. So, I have 1, 2, 3, 4, right. So, on the 4 sides I have 1, 2 on that side, 3 on this side, 4 on this side, sorry 9 dangling bonds, 9 dangling bonds over 2 sides, right. So, overall I have 4.5 dangling bonds per site. Okay. That is all right, but in general I have is this how you calculate? Okay, so the site is still the surface site, right? So in the surface site itself, so this is the site that matters for me, because I am looking at the surface 0, 0, 1 surface, right. So 4.5 per site is correct, but so per this site, right. So I am just adding more and more atoms to it, I am increasing the total surface. So I am actually creating 9 dangling bonds, okay, per this site, okay. So the way you count is a bit different, because so this is the only site of interest for me on the surface, right. So whatever is on the surface, okay. So I have increased, so here I have increased the surface energy from 5 dangling bonds per site to 9 dangling bonds per site, okay. Like that you can actually look at all the various sites, right, and you will find that so by adsorption and desorption processes, right, in site 1, 2, 4, 5, right. So these are the sites that you can take for example. Both adsorption and desorption processes are going to change the surface energy, right. So every time I am adsorbing or desorbing, I have some kind of a barrier or a valley, right. So I have some kind of a barrier, because so once I am adsorbing, if I am increasing the surface energy, right, so I have to go up the barrier and come here, right. So this is an increased surface energy. Or if I am desorbing, right, so I have to come from this state to another surface energy state, which is either here or here, right. So every time I am crossing a barrier and trying to come to a lower surface energy or a higher surface energy. So it's not a free flowing process, right. So adsorption desorption is not a free flowing process, because every time I am actually adsorption desorption is not a free flowing process, in the sense that every time I have to add dou g by dou n, right. So the g, this is the g of the surface, okay. So dou g by dou n keeps changing, right. So if I adsorb, so dou g by dou n is nothing but the chemical potential of the surface, right. So the chemical potential of the surface keeps on changing, or wherever that site is, right, keeps on changing once I adsorb it or once I desorb it, right. So once I adsorb the second atom I have to adsorb, the chemical potential again changes, right. So this constant change of chemical potential of the surface is always going to give me barriers, and so delta mu is always a barrier, right. So once I adsorb I should desorb, right. So adsorption and desorption is not happening in sync with each other, right. So once the adsorption is a high energy process, or the desorption is a higher, so desorption becomes a low energy process, and once the next atom comes, the desorption becomes a high energy process, the adsorption becomes a low energy process. So my chemical potential just keeps fluctuating like this, and it's not a very so chemical potential as a function of time or as a function of molecules adsorbed and desorbed, right. So at every point either molecules are getting adsorbed or desorbed, right. So my chemical potential is fluctuating, and these fluctuating potentials are not very good for a nice, what is called a step flow growth, okay. So nice and flow like growth, right. So this happens in growth, but it's not very ideal for me to calculate anything using this kind of a rigid, rough sort of a growth, right, growth process. So I want ideally my chemical potential mu surface should be 0 during growth, or delta mu surfaces should be 0 during growth, right. So which means as a function of adsorption or desorption, okay. That is a very so mu versus, okay, mu versus time ideally should be like this, right. So mu of the surface, okay, it cannot be fluctuating, right. So then I will have a nice smooth flow of atoms in my growth, right. Now that is what happens at this particular position if you look at this position called position number 3, right, and this position number 3 is called a kink position or a half crystal position. Let me use an eraser and then erase everything else. Okay. So, now this position number 3, if I may, so I am going into pen, right. This position number 3 is what is called a half crystal position or a kink position, right. So, it is at the kink, right, it is at the intersection of two terraces, which is a kink, right. So, that is called a kink position, or so it is a half crystal position because so for an atom in bulk, if I am looking at an atom in bulk, right, an atom in bulk has how many bonds? It is bonded to 6 nearest neighbors, right. So, the atom in bulk is bonded to 6 nearest neighbors, whereas if you see the kink position or half crystal position, it is bonded to 3 nearest neighbors, right. So, 1 that side, 2 this side and 3 downside. Okay. So, 3 nearest neighbors, right. So, half of what a crystal should have, the coordination number is half of what a crystal should have. So, it is called a half crystal position. Okay. So, half crystal is a special position, right, and that is site number 3, right. So, refer to the presentation, and in that site I have 3 bonds, 3 dangling bonds and 3 bonded bonds, right. Now, I adsorb or desorb, right. So, let us say I adsorb onto site 3. Okay. So, once I adsorb onto site 3, right. So, I am sort of control Z it. Okay. So, once I adsorb, once an atom comes and adsorbs here, right, it is as if nothing has changed, right. So, it is an infinite crystal, an atom has come and adsorbed here, right. Okay. So, I have to, let me use a different pen. Ink color can be black, right. So, now this black atom has come and just adsorbed at that position. Okay. Alright. So, now after this has adsorbed, how many dangling bonds are there? Again I have only 3 dangling bonds. Did the surface energy increase? The G surface, did it increase? No, it did not increase, right. Okay. So, any adsorption onto site 3, there is no increase in the surface energy. Okay. The total surface energy, G surface. Okay. Okay. So, this is not specific surface energy, this is not surface energy per unit area, right. So, this is a total energy coming because of the surface. Okay. Similarly, any desorption is also not going to change G surface, right. So, ideally a good position for let me see if I can draw it. So, this is my kink position and that is a special position. So, if I look at dou G surface by dou n, right, that is equal to 0, right. So, during growth so I can keep on adding atoms and subtracting atoms from this position, right. So, I can so perhaps add 1 atom here, okay. So, if I add 1 atom, right, it is as if nothing has changed, right. So, I am again exposing 3 surfaces, right. So 3 dangling bonds and nothing has changed, right. So, I can start adding more and more atoms to these kink positions or delete more and more atoms from the kink positions. Adsorption and desorption can happen from the kink positions. Okay. So, atoms can just come and sit here, more atoms can come sit here, sit here, sit here, until this line is finished, right, and then they will catch another kink somewhere else, and then so atoms can just flow and so on and so forth. And this sort of a growth where atoms are just growing line by line by line by line, right, so that it is actually propagating this step forward, right. So, this step then starts moving more and more forward by atoms getting attached to this kink position. This sort of a growth mode is what is called step flow growth. It is a very nice mode of growth, almost never it occurs, right, in all the crystal growth that we do, but this is the most ideal type of growth that can happen, right. So, the what is called a step flow growth. So, if atoms get adsorbed and desorbed at the kink positions, right. In this mode of growth, dou G by dou N is 0, which means the chemical potential or the changes in chemical potential, dou G surfaces, right. So, with more adsorption or desorption, that is equal to 0. Okay. So, as a result so I have a smooth flow of atoms, right. So, now although so this is fine, right. So ideally so I want atoms so to migrate towards the kink positions, get stuck there, right, and if atoms are getting stuck at the kink positions, I can have what is called a step flow growth. Okay. So, it is probable, most likely the atoms are going to get stuck at the kink positions, but it is the atoms getting stuck at other positions is not completely improbable event, right. So, all this so once you look at the atomistic picture of growth, it becomes very statistical in nature, right. So, what is the most probable event? Most probable event is for atoms to go and get stuck to a kink position, for the atoms to come out of the kink position, because I am not expending any energy in doing this, right. So, atoms are getting stuck, atoms are coming out, right. So, I am not expending any energy in either moving the surface or removing the surface. Okay. I mean, so there is some change in energy when the atom comes and gets adsorbed or desorbed from the gas phase to the solid phase, right. But in the solid phase itself, right. So, when the solid phase itself is growing or receding, which is adsorption or desorption, in the adsorption or desorption phase to this kink position, there is no extra surface energy spent. Okay. So, the same surface energy of the initial kink is what gets carried on. Okay. So I get a smooth flow as a result so that is more probable, but that is it is more probable does not mean that always happens, right. So, you can sometimes have atoms coming and getting stuck here, okay, that is also possible. Okay. Sometimes atoms can just nucleate here. I will show you more types of growth where atoms can just get nucleated here, right. So, it is not necessary in my like site 1, site 5, all these are probable, they are not improbable, right. But the most nice way of growth happens when atoms go and get stuck at the kinks. Okay. All right. So, now to do some thermodynamics, right. So, we look at this step flow growth as close as possible to quasi equilibrium, right. It is still growing and receding, but still so it is doing it one by one, right. So, it is a nice step flow growth. Okay. So, now so if I want to look at equilibrium, equilibrium condition is equilibrium of gas phase with solid phase, right. So, then I am going to say that mu of that atom in the gas phase should be equal to mu of the same atom in the solid phase. That is what defines the chemical equilibrium, right. And solid phase, how do I estimate the mu of that atom in the solid phase? I look at mu of that atom in the gas phase, alright. Okay. Now, so in general mu has a delta H component plus T delta S component. Okay. Now, delta H component is the enthalpy. Now what enthalpy is this? This enthalpy is what is the heat released when an atom, or heat released is negative of enthalpy, right. So, it is an endothermic process, sorry, exothermic process. When an atom goes and gets stuck to the kink position. Right. So, that is what is called the so that is the exothermic reaction, right. And what is that? That is nothing but it is the work, So, okay, so how much heat is released when atom goes and gets stuck there, right. So, it is the work done to get an atom stuck to the half crystal, or sorry no, so I have to remove an atom. So, work done to remove an atom to the half crystal, right. So, the negative of that rather, because it is an exothermic reaction. Okay. So, I have what is called phi half, which is the work done to get an atom stuck to the half crystal. Now, what is that? What is the work done to get an atom stuck to the half crystal? This thing we have calculated earlier, right. So, so that is just 3 times psi 1, I have to make 3 near neighbor bonds, plus 6 times psi 2, 6 second near neighbor bonds, plus again 4 times psi 3 for third near neighbor bonds. That you can sort of start counting, right. So, how many first near neighbor bonds am I making, how many second neighbor bonds am I breaking, how many third near neighbor bonds am I breaking, right. So, and then I have plus the dot dot dot, but so all these things, the higher order terms I can just neglect, because this is already 1% or of psi 1, right. So, I will neglect the rest of the things. Okay. So, delta H essentially it is an exothermic reaction is minus of phi half, which is equal to minus 3 psi 1 plus 6 psi 2 plus 4 psi 3. Okay. So, that is so when an atom gets stuck onto my kink position, I have some heat that is released. What is that heat that is released? It is an exothermic reaction, right. Solid to vapor, vapor to solid phase reaction is an exothermic reaction. I have when atom gets stuck, it releases heat. Okay. So, once the atom goes into the vapor solid phase, it bonds, and this bonding is nice, it likes its bonding, so it releases heat, right. Although it is only bonding to the kink position, it is not going inside the bulk and bonding, it is bonding on the surface at the kink. Okay. So, that is the work done, so phi half is the work done to do the converse process, which is to remove an atom from the kink position. Okay. So, that is 3 psi 1 plus 6 psi 2 plus 4 psi 3, but conversely when an atom gets stuck, this is the amount of heat that is released. Okay. So, that is my delta H. Okay. And in a gas, right, so T delta S, this term is the entropy term, and that is simply so that is just kT ln pi. This we have derived earlier, right. So, for a single species, what is the delta S, the mu I, or the SI, SI is for that element, what is the delta S, right. So, that is kT ln pi. Okay. All right. So, in that sense, then I have the mu of the crystal, and I have atom that is going into the crystal, that is at equilibrium, that is mu in the gas of the same atom, this is at equilibrium. Okay. That is equal to minus phi half plus kT ln pi. Pi is the partial pressure of gas in the gas phase, right. So, this is for the gas phase, but since atom crystal is in equilibrium with the gas phase, this is mu atom in the crystal is equal to, here I am taking the special position, half crystal position, that is what allows me to calculate things, right. So, the assumption is, okay, so in a half, eventually these atoms will make their way to half crystal positions, they get stuck there, and then they will start growing from there. Okay. Which is fine, which is reasonable, because most of these atoms, so as you can see, they get stuck at the kinks, right. So, or they come out of the kinks, that is the easy process, right, rather than plucking it out, or rather than so them getting stuck somewhere else, so they can come, so there is a terrace like this, they can come like this, hit the terrace, they go here and then hit another terrace, and then they can get stuck there, right. So that's and similarly, so that atom, it's easy for it to come out and then go out into the gas phase, right. So it is okay to consider that position as a special position, and if I have the complete growth happening through only those positions, then that's a very smooth flow, that's called a step flow growth, right. And in that position, right, so we have so I'm actually saying from the gaseous phase it is going into the crystal phase, but not to any position in the crystal phase. I am saying it is going to that particular surface position on the crystal phase, right. So that would emanate, that will give out a heat of minus phi half, okay. So that's my enthalpy term, and then I have an entropy term which is just kT ln pi, right. So this is the entropy of that particular species in the gaseous phase, right. So that is that particular atom that is coming and getting attached, okay. Now what I have done here secretly, even without telling you, is I am doing thermodynamics at an atomic scale, right. So I am actually writing mu of course mu is defined per atom, yes, but this is of that particular atom that is going and getting stuck to the kink position, right, and I am going to generalize this, right. So this is so thermodynamics is typically considered bulk thermodynamics. No, here I am actually so I have this atomistic picture in mind that is happening, and based on this atomic picture I am actually writing thermodynamics at an atomic scale, okay. So that's something that needs to be appreciated, okay. So in this case, all right. So and then so we know how to evaluate this phi half. Phi half is just the energy to break that bond or make that bond, and so when does deposition happen? The question is, when does deposition happen? So if once I write this reaction, I can say deposition happens when mu gas is greater than mu atom of the crystal, right. That means Pi should be greater than Pi equilibrium. So the only thing that changes, because half crystal position enthalpy is going to be the same, I detach atoms from that half crystal position. The only thing that can change from environment to the solid is the Pi, right. So at Pi equilibrium, this mu atom crystal is in equilibrium with the gas, but at a higher partial pressure, right. So that is why I should increase the partial pressure of gas so that I get more deposition, okay. So Pi greater than Pi equilibrium, I will have adsorption events are more than the desorption events, okay. So essentially what I am saying is gas to solid, right. So if mu gas is greater than mu solid, this reaction goes forward. Now I have a recipe to evaluate that reaction. I am just saying that so I am giving you a synthesis recipe. Synthesis recipe is calculate Pi equilibrium. So once I know what is the equilibrium Pi, where mu I gas deposition does not happen really, right. So it is just at the verge of equilibrium. Pi equilibrium is this half crystal mu atom at that crystal plus phi half, right. Now if pressure is greater than Pi equilibrium, that is when the gas has higher mu and I will have more and more deposition, right. So on the crystal, right. So adsorption then dominates over desorption, and I will have a smooth step or a growth of things that are on the kink positions, right. So then adsorption will dominate over desorption, okay. So it is not the but whether I am adsorbing or desorbing, I am not changing the mu of the solid, right. So the mu of the surface is still the same, okay. Okay, so that is that is what I wanted to discuss about the special position called the kink position, which is very useful in crystal growth, right. To keep thinking about the kink position. Maybe in reality it is not always true, especially when the growth goes a bit non-equilibrium, right. So I am depositing lot of material at the same time the flux is large, then I can have nucleation events, or I can have events which are not happening at the kink position. But if I do it in a quasi static way, right, so the gas flow is coming slow enough, I give enough diffusion time, then these atoms most likely go and get stuck on the kink position, and from the kink position the growth starts to happen, right. So, and that's a nice way of growing crystals, or so in this case films, let us say, right, and that will happen when the atmospheric pressure or the vapor pressure of the atom that is getting adsorbed, that should be larger than the equilibrium pressure. That's just a simple thermodynamics. And how do you evaluate equilibrium? You evaluate equilibrium from the half crystal energetics, right. So, the energetics of the half crystal. Okay. So essentially that's what it is. Okay. So, from the energetics of the half crystal you evaluate what the equilibrium is. Alright. So, with that let us stop this discussion on half crystal, and in the next class we will actually look at what will happen, this idea of vicinal surfaces and singular surfaces, right. So, so you have all these terraces and these kinks and other things forming, right. So, that is also to minimize the total surface energy. So, why is that the case, right. So, why can't I have a surface which is just miscut at 0.1 degrees, right. So, we will see that, and from there we will look at what are the energetics of surfaces in general, right. So, energetics of surfaces are not continuous, right. So, in that sense, so I can, if I go from 001 to 110, my energy is just not going to scale nicely and linearly monotonically up, right. So, at 001 it is going to be minimum, at 110 it is again going to be minimum. So, I will have these cusps and so discontinuities and things like that, right. So, it is not a very good looking graphs, or very continuous graphs, the what is called the polar plots of surface energy, right. So, we will look at that, we will look at the anisotropy in surface energy in solids in the next class, and then so probably by the end of next 2 classes or something we will see how to actually calculate the equilibrium shape of a crystal that is forming, right. So, by itself, okay, through what is called Wolf construction. Okay. So, with that let us conclude this class, and I will see you again in the next class. Thank you very much.